All right, welcome everyone to our live panel on Subsystems Part 2. We've got a lot of great talks for this, and a lot of great panelists for this panel. Like all of our panels, this whole conference is free to attend for everyone, and that again is in big part to our sponsors. For this session, we would like to highlight one of our gold sponsors, LinkSpace. LinkSpace does have an exhibit with us, and their exhibit will be open this afternoon. So I would highly go visit their exhibit page and then connect with them in the Zoom breakout rooms starting at 2 p.m. Pacific time. With that, I'd like to introduce the moderator for this panel, and that is Dr. Pauline Four, who is the Cal Poly CubeSat Laboratory Director and Assistant Professor at the Aerospace Engineering Department here at Cal Poly. Dr. Four has been developing and managing international small satellite projects for the last decade, putting an emphasis on applying systems engineering's best practices to small satellite programs. Dr. Four.
Thank you, Ryan, for the introduction. Welcome, everybody. Welcome to our panelists. So you must know the music by now. We will start with a short round of introduction from the panelists, with me asking questions, and then we'll open the floor to the rest of the audience. So let's get started. And I guess, hold on, I have to review my order since things have changed now. So we're gonna start with Miguel Vazquez from GHV Technology. So Miguel, if you please would like to introduce yourself, and a short summary of your talk.
Okay, thank you so much. My name is Miguel Vazquez from GHV Technology. I'm Managing Director and co-founder of the company. Our company is focused on power subsystems for space applications. So we comment briefly about our experience and heritage on power subsystems for CubeSat and small satellite. Thank you.
Thank you, Miguel. So my first question for you will be for new CubeSat developers who might be looking at do some shopping for EPS services or solutions. What are your advice for them on what they should ask suppliers to make an informed decision and technical decision on their choice for EPS?
Absolutely, it's an excellent question. I think that at the end of the day, talking about power and talking about EPAs in general, CubeSat for sure is a standard. We know very, very well. But at the end of the day, some of the requirements of the missions and the platforms are usually different, one of them. So it's quite difficult to find a complete standard component for power and for solar panels, and for sure for EPS. So we recommend to analyze deeply the specific requirement for each mission, each platform, and then for sure to look for the best solution to tailor to adapt to this requirement. I think the standardization for sure is a relevant element for the integration in people, but at the end of the day, some of the components require some customization.
Thank you, Miguel. And my second question for you, and you touched also upon it during your presentation, is that we've seen that growth of CubeSat and the diversification of the mission that now requires a higher power. And so could you please address how you're implementing ESD countermeasures in your system?
Yes, absolutely. Yes, in some of our missions, we develop ESD environment quite relevant. For example, in some GTO missions or in NEO. This point is relevant when the radiation is high, particle radiation is high, and for sure there are different approaches are possible to introduce in the solar panels when this requirement is appear in the mission. Some coating on the solar cell is possible to apply to reduce the effect. Some conductive coating, and in addition to that, to the solar panels. So it's possible to mitigate this point using the proper material and the proper coating according to the requirements. Yes.
Thank you very much, Miguel. We will be moving on to our next panelist, Thomas Yan. So Thomas is the co-founder and CEO of Tensor Tech.
Hello.
And today he will share with you the research outcome of his spherical motor studies, which he has been working on for nearly 5 years. So Thomas, yes, if you would please provide a further introduction and a brief summary of your presentation for the audience.
Okay, a 2 minutes summary, right?
Yes, overall.
Okay, so Tensor Tech focus on the attitude control system for satellites. And our technique is a little bit different compared to the traditional solution, which we use a reaction sphere, and it is consist with a spherical motor, which is capable of spinning in multi-axis. So it is capable of replacing multiple reaction wheels from a satellite, and to provide lower volume and a lower power consumption, and also lower weight. So besides the reaction sphere, Tensor Tech also provides the integrated ADCS solution that includes the attitude sensors such as fine sun sensor, magnetometer, and the gyroscope, and also the reaction sphere and magnet talkers as a integrated ADCS solution for the people who are who wanted to build their own satellites. Yeah, this is a quick introduction about our company and what we are doing right now.
Thank you very much, Thomas. My first question to you, when I watched your presentation, I was wondering if you had been able to evaluate the magnetic noise of your SES solutions, and how did that compare to standard reaction wheels and magnet talkers solutions?
You mean the magnetic noise from
Yes.
the reaction wheels, right? Okay, so there is a nickel-based alloy made this kind of a shell. The shell is covering up the exterior structure of our reaction sphere. So this kind of nickel-based alloy, it is has a high magnetic permeability, so it can reject the magnetic flux coming out from the reaction wheel to interfere the performance of other electronic systems on the satellite.
Thank you, Thomas. And a next question I have for you is, you mentioned in your presentation that the torque output accuracy, especially for the XY axis, depend on the tilting angle. And so that made me thought of, do you have some requirements from the structural interface standpoint to mount your system?
Oh, you mean the mounting of the system? Okay,
Yes.
so usually we will define a attitude control system frame, and then also there will be a spacecraft frame. So usually what our attitude control system can guarantee the pointing accuracy is based on the attitude control system frame. And then so for the mounting issues, we will have a locating pin on our attitude control system. So when our customer, they are trying to integrate our ADCS into their spacecraft frame, and there will be a locating pin to make sure that its angle alignment won't be larger than, I think it's 0.1 degree based on the specification of the locating pin. So, but our pointing accuracy will be based on the satellite frame, ADCS frame, and then our users can convert it to their spacecraft frame pointing accuracy via the locating pin, the specification of locating pins.
All right, thank you very much, Thomas.
But this is a great this is a good question, because this occurs many times that when we are discussing with the specification with our customers.
Yes, yeah, that's kind of the hurdle of developing independent subsystem, is that you need always to consider the integration with a host. And so this kind of problem rise a lot. So thank you for sharing your product performance on that regard.
Thank you.
We will next be moving to Marloun Sejera. So Marloun, if you please would like to introduce yourself and provide a brief summary of your presentation.
Good afternoon, good morning, everyone. I'm Marloun Sejera, a graduate student from Kyushu Institute of Technology in Japan under Professor Menbucho of Lasin. So my presentation is about programmable interface board, or Backplane, which connects all the subsystems and missions of the CubeSat. So it's programmable in a sense that you can reuse the Backplane from one payload to the other by just programming or rerouting the payload to the subsystem by programming it. This has been proven working in space in 1U CubeSat, but hasn't been proven to higher CubeSat platforms. And we have this 6U satellite here in QTech that we put on the programmable interface Backplane, and it's scheduled to be launched this year. Thank you.
Thank you, Marloun, for the introduction. My first question to you is, so this CPLD, this complex programmable logic device, has been implemented in the BERT 3 project, and now we are at BERT 5. Could you describe the evolution of and the implementation of that CPLD from BERT 3 to BERT 5?
Basically, it's not much of a change. The mission become more complex than BERT 3. They added more missions. So it's just a matter of utilizing the CPLD to accommodate those mission payload of that BERT 3 1U CubeSat. BERT 5 1U CubeSat, I mean. All
right, thank you. And then at the end of your presentation, it was kind of ending on a cliffhanger and a lot of suspense, where you were starting mentioning the FPGA. So I was wondering if you could expand a bit more on that FPGA, the performance, if you have a plan to fly it, what is the mission about, anything you're allowed to share with us today.
Okay. So when I was about to submit my abstract, that part is just a concept mission. The idea is that our BERT platform can only accommodate basic data communications like UART as well as SPI. But as we move along to more complex missions, we are to cater other communication protocols like I2C, CAN. And so the target of that part is to accommodate payloads wherein the communication, the data communications is not UART as well as SPI. So our subsystems here make use of UART and SPI. So in order to bridge that BERT's subsystem or bus system to the requirements of the payload. So that's the target of that end of the presentation.
All right, great. Thank you for the insight. All right, our next panelist is Andrew Santangelo. And Andrew Santangelo is the Chief Technology Officer of SciZone and Principal Architect of the LinkStar radio system and CubeSat environment. Andrew has supported the design and development of numerous satellites, UAVs, near-space concept systems, and commercial flight systems. Andrew is a lifetime associate fellow of the American Institute of Aeronautics and Astronautics, and is a founding chairman of the AIAA Small Satellite Technical Committee. In recognition for his efforts in the aerospace community, Andrew has received in July 2005 the Distinguished Service Award from the AIAA. So Andrew, you know the drill. If you'd like, if you want to add to your own description, and please present briefly your presentation.
Yeah, no, you covered the bases really well, Pauline. Thank you very much. Actually, my paper, my video, I guess, that I presented for the workshop is the LinkStar Cybersecurity Sandbox. It's a cybersecurity CubeSat sandbox, a platform to test CubeSat vulnerabilities within a small satellite community. So that covers CubeSats, right? But actually, I should say it also covers large satellites, medium satellites, any satellite, right? So CubeSats, let's focus on that, are becoming ubiquitous in low Earth orbit with operators ranging from the US government to commercial space to university teams like Cal Poly, and even hobbyists. And however, CubeSats are vulnerable to a range of cyber attacks on the ground segment and the link segment and the space segment. And we're discovering this when we work with a range of customers. I would say DoD, I'm pretty comfortable with the level of security put on the satellites. I would say commercial, pretty much any other satellite there is, they're wide open. Let's put it that way for attack right now. And we've discovered that through our customers and applications, and of course doing our part on the cybersecurity side. So the problem is for a university or hobbyists or even businesses, testing and understanding the range of threats to all segments on a CubeSat mission are daunting, especially for teams not well funded. So they don't really worry about requirements. They always give lip service to software. They think, oh, we got software, we're good. And that ends up being the downfall of the mission. Now you have to add this other layer of cybersecurity, which I feel, you know, we were worried about orbital debris the last few years. I think cybersecurity is going to be a roadblocker for many CubeSat, if not CubeSat missions. So with that in mind, SciZone, in partnership with AIAA, the Aerospace Cybersecurity Working Group, and NASA actually created the LinkStar Cybersecurity CubeSat test platform, a sandbox to test vulnerabilities in a CubeSat. And it's an actual CubeSat we have with our LinkStar radio system. So it's talking to space to and from, it's beaconing, it's full control of a satellite, has all the systems you expect in a CubeSat, except it's on the ground. It thinks it's in orbit. We didn't want to put a real orbiting CubeSat or CubeSat in orbit that you can hack and cause great peril. But this is a sandbox that the CubeSat thinks it's in orbit on the ground, where we can provide ways to look at all mission segments, both the link segment, the space segment, the ground segment, and see where the vulnerabilities are and share that with the community and provide a framework for people to use on their satellites, their CubeSats here. And again, this is providing all the segments for security. And so far, it's been pretty exciting. We did we did this at the Ascend Aerospace, where we did a hack a satellite, and we went from simple as social engineering and getting on the ground network to turning off a satellite in orbit. That was pretty breathtaking. So, and I can share that link too with everyone. And our goal is to include more from the community and to coordinate, go ahead and hack, so to speak, but we want to coordinate that and share those lessons learned. So it's not going to be everyone on the planet, but we want to invite the community, see those vulnerabilities, see what we can change, and share that to make it at least become a more cost-effective solution for the CubeSat community, because I think that's going to be a blocker for most missions.
Thank you very much for that introduction, Andrew. So my first question to you is, like, you provide me a great anchor point speaking about university and hobbyists and not funded as a DoD, basically organization. Mm-hmm. And so let's call that entry-level advice or action that that community can take with regard to cybersecurity. Do you have any advice of what type of implementations we could have when we're considering this design of our spacecraft?
Yeah, I would, first of all, the immediate advice I would give, boy, like I said in my previous session last Tuesday, I could take hours on this, but we're not going to do that. So the first advice I give, and I did this on the software side, is I tell all CubeSat missions is before we get into cybersecurity, do not underestimate the effort required to make sure your software works and you identify requirements. Software is, like I said, the downfall of missions. Now, when you consider software, you have to now consider what are the weak links, both on the ground segment. I've had teams put their sample satellite right on the internet, no firewall, no nothing. And even though it may not be hacked, nefarious code can be injected into that CubeSat, which then finds its way into space. That's a very extreme example, but I've seen that. And even just basic practices to put your CubeSat and your ground station behind a firewall, right? And not maybe have a real, give everyone the same account name, right? And its password, so and then someone leaves. And by the way, that's another vulnerability, is just leaving a terminal open. Or let's say a student didn't get, he or she got a C and got grouchy and does something, right? So there's a lot of weak points right from the ground segment on up, and you don't know what's going to happen in the CubeSat. So first of all, I would say, do not disregard software, and now consider everything you do on your laptops right now to concern about security, and what you do personally. I would consider that for your CubeSat and your ground station segment. And on that, and I think that's the real thing to consider, and start early. Don't do this. I've had so many projects where they start looking at software the last 3 months, and that's it. So at that point, tell them, if you can at least have your satellite say hello world, you're doing good.
Thank you, Andrew. Kind of a follow-up. I was glad to see your presentation, because you do insist it's not only just about the spacecraft or the space segment, it's also about the ground and the link segment. And that's something that we tend to forget about,
yes,
right?
Yes.
All these other interfaces.
Mm-hmm.
And so something I was wondering about is, have you been coordinating in particular with the links segment, like commercial services provider, with them to maybe develop some kind of standard or like best practices to then offer to the community? What is your action there?
Yeah, yes, actually we're doing that with GlobalStar. We're a partner with them. Matter of fact, our radio system certified, actually, because our radios can not only be used in space, and that's a market, it's must be used in oil rigs, right? And so now we're talking thousands of units, not just, but their security, because it goes through a satellite network, is just as, if anything, more important. You don't want to oil rig blowing up or pipeline leaking oil in the. So yeah, we are working those best practices, and we're going to be publishing more of that to cover both, again, ground UAVs and satellites, but they all work, they're all going through the same link segment, right? Going through a satellite back to the ground. Matter of fact, even with our simpler IoT based devices now that are doing two-way communications globally, a simple command to shut down your satellite, well, that's that, right? Matter of fact, in our Ascend Outer Space Hackasat, the first step was someone socially engineered, got a password, immediately was able to just log in and view everything. The second attack was changing the data to make you think the satellite was overheating when actually it wasn't, right? And just messing with the data. And of course, the third one was, well, now they had the commands, they turned off the satellite, and that was that. And one thing I also try and tell, I've always had students say this, well, why would an adversary be concerned about my CubeSat? I'm just doing a little science experiment. I'm just a student. Why will they pick on me? Well, you're a perfect use. That satellite's a perfect use. A good example is if you have articulating solar panels, they can change the drag coefficient, and if you have no propulsion system or anything, and they can redirect your CubeSat to whack into something else, like the space station or more important. And maybe even use it as an experiment, saying, okay, now we've done this, let's go to the next more challenging target to take out.
Right. Your Hackasat sounds like a fun, for lack of a better word, a fun experience for everybody who would like to join. If you'd like to put the link in the chat for people to join, please feel free to do so. Thank you very much.
I'll put down the link from the last one, email. Yeah, I'll put in the I guess not the Q&A, I'll put in the chat session, right?
Yes, perfect. Yes,
So,
the chat. Thank you, Andrew.
If you don't see it, then I'll You bet.
All right. Our next up is Matt Orvis from NearSpace Launch and Hank Voss. It looks like Hank couldn't join us today, but we'll still introduce the both of you. So Matt is a project engineer with NearSpace Launch. His roles include mission manager and systems engineer over the past 6 years. Dr. Voss is founder and president of NearSpace Launch. He is a former university professor and Lockheed Martin scientist with over 40 years experience. So Matt, if you would, 1, 2, 3, only the first time, please introduce your presentation briefly.
Thank you, Pauline. Yeah, my name is Matthew Orvis, and I think I have the distinct pleasure of being the very last presenter to go in this conference. So saving the best for last, I assume is what you were doing.
Exactly.
So yeah, work with NearSpace Launch, and I'll be presenting on some recent flight results, including the ThinSat 2 constellation, which was 30 satellites, our new troop payload, and a miniaturized GPS that we've just developed. So just briefly, NearSpace Launch, you know, we've launched over 600 systems in space so far. 130 of those have been our Globalstar connected radios, and thus far we have 100% mission success, thankfully. So crossing our fingers that it stays that way, and we produce the turnkey satellite solutions, ThinSats, black box units, and more. So the ThinSat was a 30 satellite constellation that was launched in February. This a ThinSat is basically a slice of bread. If you think of a CubeSat as a loaf of bread, a ThinSat is like a slice of those. And so 30 of these launched in a single 2 3Us, and they deployed out in a constellation. We had good results on these, but there were some issues which we discussed in the presentation. We recently launched our first troop mission. Troop is basically a new type of hosted payload that the troop bolts on the outside of a space flight deployer ring, and we can host 4 payloads at a time, basically the size of 1U payloads. This will drastically reduce the cost of getting payloads in space. So it'll be about 80,000 per payload instead of 300,000, you know, to get a whole CubeSat. And we'll be able to do about 3-month to 6-month cadence on these and have tracking and live telemetry and switch power and all that kind of stuff. And then finally, you know, we've got this big issue of satellite ID and orbital debris tracking and that kind of stuff. And so we developed miniaturizing a GPS and integrating that onto our iStar S3 Globalstar connected board, which is super small, super low power. It's like 1 inch by 2 inches by 1/2 inch. And you've got a full transmitter and Globalstar receiver on there. And so we just recently launched that and had good results. We're able to provide the satellite ID and TLE for the Sherpa spaceflight ring that we were on. So yeah, that's basically the summary of the presentation.
All right, thank you very much, Matt. Your last point is exactly where I was going with my first question. We had a lot of talk with regard to space domain awareness, and I'm going to quote Cynthia Wilson from the 18 Space Control Squadron regarding bells and whistles for ThinSat. So you just mentioned the GPS aspect. Are there any other solutions you're implementing on ThinSat to enable their clear identification and tracking over time, considering they are the slice of bread, not the full loaf?
Yeah, it's funny that you mentioned Cynthia Wilson. We've been working pretty closely with her and her team in getting a built-in data flow from these units that have the iStar tag on it, of automatically collecting GPS data and shipping it off to 18th Squadron to help them with really early satellite ID and tracking. And they've been on a few proposals with us, and are, as far as I know, very excited about this, what we're doing with this. Regarding the ThinSat, so we had GPS on all of them that was connected to the 18th Squadron. It was kind of a test to see how well this was going to work. We also developed the ThinSats with a form factor and that was just at the lowest range possible for what they expected to possibly be able to detect with tracking. As well as putting them together in sets of more than one to be able to increase that. And it was run almost as a test of that ability. And as far as I know, it was better than expected, at least, although it's definitely not going to be as easily detectable as a larger satellite, even as a 1U.
Yes. All right, thank you for that insight. The next question that I was wondering about, since you're deploying so many ThinSat at a time, what is your approach to handle the signal interference between of those? How is that handled with that thread of ThinSat?
Yeah, that's a great point. They only have, they've got a few different receivers on board, which haven't, but don't show interference. The transmitters are all just one-way transmitters, so they don't require handshaking with the GlobalStar network. And because of the protocol being used between those satellites and the GlobalStar network, that network is built to have many thousands of units transmitting at the same time. So to just have 30 or 60 at a time transmitting isn't providing any undue load on that particular system.
All right, great. Thank you, Matt. And thank you all panelists for going through that first round. We have now a few questions from the audience. I'm going to start with a question to Miguel. What may be a better solution to build CubeSat from COTS or, oops, something got upvoted, and sorry, I cannot read anymore. Build CubeSat from COTS or choose a turnkey solution, then develop the appropriate software for the control of the CubeSat for academic purposes?
Okay, thank you for the question. I'm not specialized on software on CubeSat, but as we commented before, we think that the customized solution for hardware of solar panels and EPS sometimes is required, take into account the requirement of the missions. So take into account this point, and for sure take into account that CubeSat is in general, the developer try to accommodate the cost solution and standard solutions. For example, in our company, we develop some standard products compatible with a standard platform and a standard deployer. But for sure, sometimes it's not possible to use standard products that is requires some customization, specific talking about solar panels.
Thank you very much, Miguel. Our next question is for Thomas. Your reaction sphere replaces a much larger set of 3 or 4 reaction wells, saving valuable volume. Does this mean that the total angular momentum of your system is less than traditional systems? And then does your reaction sphere needs to be desaturated more often than a traditional system?
Okay, actually, I'm typing my answer right now, but it's okay that I can just answer it right now. And so the maximum angular momentum storage of our system is 10 MNMS. So comparing to like the Blue Canyon's XACT15, which weighs around 800 grams, and its maximum angular momentum storage is 15 MNMS, and then our system weighs 400 grams, and or compared to the ADCS provided by the CubeSpace, which weighs around 1,000 grams, and its maximum angular momentum storage is also 10 MMS. So our products aims for the nearly the same performance on attitude control comparing to our competitors, but with less volume and also power consumption. So and regarding to the desaturation issue, actually we also have magnet talkers on board. So how often it has to be desaturated is actually a complicated question, and it depends on our customer's operation. Like when it needs our satellites to constantly accelerate in a certain direction, then it will need much more often the saturation. But if it's a maneuver activity or a maneuver command that has a backwards and forwards of the command, and then we will require less frequent desaturation. Yeah, so it's much more depends on our customers' command or the dragging profile of the satellite that has occurred on orbit.
All right, thank you. And we have another question for you since I have you on the mic. Assuming you have the same volume and power as a traditional reaction wheel-based ADCS, how does the pointing accuracy compare?
Okay, so when we are talking about the pointing accuracy of a ADCS, there are two parts. The first one is the determination accuracy, which we call it pointing knowledge. And the second one is the control accuracy. So usually when you only install the magnet talker, the control accuracy, the optimum control accuracy of a magnet talker is around 5 degrees. But if you install the reaction wheel-based attitude actuator, then it usually can reach to arc-second level of the pointing accuracy. So usually the overall performance of an ADCS will then depends on the attitude sensors. So like traditionally, if you only have like magnetometers, gyroscope, or the fine sun sensors, then usually the pointing determination accuracy is around 0.1 degree to 1 degree. But then if you need to achieve a better accuracy, then a star tracker would be required. So like the standard product now TensorTech offers is without star tracker. So its pointing accuracy will be ranging around 0.1 degree to 1 degree. That depends on your orbit. And then if our customer requires a better accuracy, then our system is compatible with installing another star tracker. Then we can achieve arc-second level of the pointing.
All right, thank you very much, Thomas. Our next question is to Andrew, and I think you were also starting to type, so sorry for the interruption.
Yeah, I'm starting to type, no problem, no problem.
So I'm just going to read the question. I'm not sure if the audience can see or not. What most CubeSats, being low cost, simply do without cybersecurity, regardless of the consequences? No matter what they should do, I'm asking what they will do in practice. Thus, will it be more feasible to prepare to deal with the consequences and there being a bunch of hackable CubeSats in orbit? That's a tough one.
Can you hear me okay?
Yes, we can hear you now.
Hello? Yeah. Okay, good. Lost the link for a second. That's a loaded question. First one, I think from a university perspective, yes, CubeSats are relatively low cost. But obviously, if we go commercial and government, low cost begins to go out the window, right? So that would be and that's where we really have to address just that segment that is low cost, and I should say low budget. So yes, the first step is, let me put it this way, if it's a government mission, NASA or DOD, they're going to require, no matter what, some form of cybersecurity system. That eventually will trickle down to the university level, which I can see that as being a roadblock, that where the government's going to go, no, we're not going to let you count on the consequences. We're going to want to do something, especially if there's any form of control on your CubeSat or small satellite. And that's part of things behind the whole Sandbox, is to provide these tools to make it more lessons learned, so you don't have to redo it and learn it, and then to provide the tools. A good example is for our LinkStar tracker with our GPS tracking going on CubeSats, small satellites, whatever satellites. We're now rotating in artificial intelligence and machine learning tools to the CubeSat, so it becomes aware of a fault or a cyber attack before it actually happens, like something is going on, and then to open that up to the community. So when so right now you have our LinkStar tracker with Globalstar that's tracking CubeSats, small satellites, and whatever. Actually works on boats and cars and planes too, but it's a CubeSats. There, like I said, we're adding that layer and we're implementing that into the Sandbox where people can, where it then starts learning, right, that these attacks, and then hopefully trying to make it open source, as open as possible, so that when someone implements in their CubeSat, it's low. They don't have to worry about, well, the consequences. They're prepared to deal with consequences before it happens. And that's why when things, again, we're hoping with opening it to this community at large, including our work with NASA JPL and the cybersecurity community working group. And of course, this whole attendees here of the workshop here. So, and right now we got a first test for the AI-based systems. Hopefully, we'll see how launches go, where it's going to, we're not going to do any cyber text, don't worry, in space, nothing like that. But those sort of tools going in orbit here in the next 3 months, we're hoping. We'll see.
All right. Another exciting.
That answers the question. But I don't know if it answers the question, but I think we have to get out of the just deal with it afterwards, because if you have several hundred CubeSats that are vulnerable, or 1,000, that's not good. That's my 2 cents.
Thank you, Andrew. Marloun, thank you for answering the question. I wonder if you wanted to talk a bit more about, so the question, sorry, could the same technology that you presented with the CPLD be used within the bus on subsystem to subsystem interfaces? And you mentioned that yes, but you said that for you, you mostly use it between the bus and payload. So could you expand a little bit on that, maybe on the rationale?
Yes. So the programmable interface backplane is basically used for rerouting lines between the subsystems, for example, the onboard computer to the payload. So that's the main objective of configuring it, so that the platform can be used from one payload to the other. But there are lines between subsystems that we can also be implemented with CPLD. So for example, ADCS, between ADCS and onboard computer, we implement CPLD on it, as well as the umbilical, or when you want to program the onboard computer and other MCUs on your subsystem externally. So we implement configuration using CPLD on it.
All right, thank you, Marloun. And last question before we go to closing, from me to Matt. Matt, in your presentation, you mentioned the troop system or the troop platform for hosted payload. And you mentioned that troop 2 is already full, but I was wondering if you could give information to the community if they would like to apply for troop 3, 4, or 5, or whichever number. How do they go about it?
Yeah, thank you. That's a great question. Yeah, troop 3, 4, and 5 are already open and available and are starting to be filled. So there's plenty of slots open, and if we fill up, you know, say troop 3 fills up and there's still more people that want to fly, and that flies in December, we can just put more troops on a single launch, you know. And so it's not like it closes and you're stuck 6 months later. We can just add more troops to a single to a particular launch. So those are open. There's a 3 to 6 months cadence. I mean, just send me an email. I think it's on my presentation, and we'll get you started in that pipeline. It's super easy. It's meant to just have a single payload interface with power and data. You'll get an emulator with it to be able to test your interface before delivering it, and it literally just slides into the side of the unit, and the connections made, and that's pretty much it, you know. And then there'll be I don't think I mentioned, but it has an orbit lifetime of about 8 years, and so for that 8 years you'll be able to have this live data link from the satellite, collecting your payload data, and it's going to be collecting that along with some sensors on board as well. So there'll obviously be GPS, but there'll also be energetic particles, plasma, IMU, temperature, that kind of stuff. And you'll have online access to the data as well. So you just log in and see the data live streaming right there.
All right, great. Thank you for the additional information. And if you'd like to put your email into the chat, feel free to do that too for the audience. All right, so that concludes our panel. So I'm going to handle it back to Ryan for closing the panel officially.
Thank you, Pauline. And thank you to all of our panelists for that great discussion and sharing your work with us. It's a very, very exciting conversation, and look forward to following the progress of all your projects and subsystems in the future. So thank you, everyone, for attending this session. Our next session will start in about 14 minutes, and that'll be a workforce development panel discussion. So please join us. Thank you.